Hello, everybody. I have my tea. I've gathered my inner mental resources for these notes. And I made this nice note sheet for you, but then the copy machines are all down. So instead of this, we're going to do notes just on a blank sheet of paper. But I wanted you to know these notes were ready. They were ready for you. So we've talked about fitting a curve to points before. Let's remember what it was we said and then go one step further. So let's pretend we want to fit an exponential like y equals 2 to the x to a point, such as 10, 5. So we sort of had a two-step process. One was we added a parameter that represents a transformation. So for example, this parameter k represents a vertical shift. Or let's do another one just to show that there's variety that's possible. We could add the parameter up here, in which case it represents a horizontal scaling. Just as a quick exercise, why don't you pause the video and see if you can solve for the two k values that would take that curve through that point. Go ahead and pause. Okay, here's some solutions. So we plug in what we know to solve for what we don't know. So what we know is that we want the curve to go through the point 10, 5. So the y value is 5, the x value is 10. And then we can solve for the k value that we don't know. So k is 5 minus 2 to the 10th. And then we can rewrite our original equation as y equals 2 to the x plus 5 minus 2 to the 10th. Great. And you were just fine at this on a previous test. On this side, if we plug in a y value of 5 and an x value of 10, in order to solve for k, we take log base 2 of both sides to undo that exponential. And then we divide by 10. So k is 1/10 log base 2 of 5. And then we could rewrite our original equation this way. 2 to the power 1/10 times log base 2 of 5 times x. Okay, so before we take our next steps, I just want to be really explicit about what are we really doing when we add a parameter, and what are we really doing when we plug in what we know and solve for what we don't know. So when we add a parameter, what we're doing is adding a degree of freedom to the equation that lets the equation change in a very specific way. So for example, if I'm going to add k to the outside, k represents a vertical shift. And what's depicted here is all the curves with integer k values between -5 and +5. So you see all the different vertical shifts. But then if I was going to add k in a different place, like let's do a multiple of k up here, now it's depicting all of the curves that have been horizontally scaled by integer values between -5 and +5. Or we could visualize vertical scaling. And so hopefully this looks like all the vertical scaling between -5 and +5. So that's what we're doing when we're adding a scale factor or any type of parameter, is we're giving our family of curves a degree of freedom. And then what are we doing when we plug in some coordinates? So you've seen plugging in coordinates in two different circumstances that I'm going to call asking and telling. So let's pretend we have a particular equation, such as y equals 2 to the x minus 32, for example. So if I'm going to plug in the coordinates 10, 5 here, that's like I'm asking a question. Do these coordinates make that equation true? And remember, any pair of coordinates that does make the equation true is going to be a point on the curve defined by that equation. So let's go ahead and plug it in, and this one's going to be false, but let's just make it be false. So 2 to the 10 minus 32. I'll put a question mark here because we are asking the question, are these two sides equal? And the answer is clearly no. So we'll say 5 doesn't equal 2 to the 10 minus 32. So not a point on the curve. All right, so here plugging them in was asking, is this a point on the curve? What if we have the parameter 2 to the x minus k, and now we plug in 10, 5? This is us telling the equation that we want it to be true, that the left side equals the right side when you use the coordinates 10, 5. So now we're saying, yes, these two sides are equal for some value of k. We just don't know what the value of k is. And so what you're doing when you're solving then is you're figuring out what's the value of k that makes it true. So if we want to write some notes, telling the equation, it is true for some k, but which k? We have to solve for it. All right, so you might have known all that already. I just wanted to be explicit about what are we really doing when we add a k and then plug in and solve. So now let's take it a step further. Let's say we've got our same curve, but we want to fit it to 2 points, 5, 10, and 8, 3. And I think it always helps to kind of visualize these things. So 5, 10 might be up here-ish, and 8, 3 might be kind of down there-ish. Okay, so let's imagine a couple of different ways we might do this. So first, try and rewrite this family, but with a vertical scaling factor and a horizontal shift. And then before you solve it, go ahead and write the same equation, but this time with a vertical scale factor and a horizontal scale factor. So pause it, write your two equations. Okay, here we are. So let's see, vertical scale factor, I'll multiply on the outside, and you can use whatever variables you want. I'll use a and b. So this is vertical scaling, and then horizontal shifting, I'll subtract by b up here in the exponent. For this one, we'll have a vertical scale factor of a, and then a horizontal scale factor of b. So just like last time, a and b are introducing now 2 degrees of freedom. So my exponential family could be stretched vertically in any way, but any of those could also be shifted horizontally in any way. So now there's like a whole lot of possibilities for what this could look like. And when we're plugging in our 2 points, we are saying we want it to be true that that when x is 5 and y is 10, it makes this equation true. So we're asserting, yes, this is going to be a point on the curve for some values of a and b, and then we're going to find out what those are. So let's go ahead and plug things in. So here y value is 10, x value will be 5. So that's one equation. Let's plug in the other one. So when y is 3 and x is 8. So now we're saying with these two equations that we want it to be true that those coordinate pairs make the equations true for some values of a and b. And we want the same values of a and b to make both of these equations true at the same time. And so that's just another way of saying we're going to solve the system of equations. All right, so a lot of people like to do this by, and by people I mean students, a lot of students like to do this by substitution. So you'd isolate a, and then you'd plug in a here. I'm going to show you a different way to do it. And why don't you sort of follow along with me? So rather than adding both sides or subtracting both sides to eliminate, what if we divide the top equation by the bottom equation? So I'll get 10/3 on the left, and here I'll get a 2 to the 5 minus b over a times 2 to the 8 minus b. So now a divides a to become 1. So we've eliminated a by doing this division. Let's solve it the rest of the way. So you might be tempted to kind of multiply over here, but then you'd have to take logarithms and it would get kind of messy. So instead, let's use this exponential rule, which we haven't reviewed recently, but I think that you know it. If we've got, for example, I don't know, 5 to the a divided by 5 to the b, that's the same thing as 5 to the a minus b. And we're gonna prove that this kind of simplification rule is true at length later on. But for now, let's just remember that that's a thing that you've seen. So applying that rule now, we've got 2 to the 5 minus b minus 8 minus b. Let's take log base 2 of both sides. And let's simplify this top part. So 5 minus 8 is -3. Whoops, -3. And then negative b minus opposite b is negative b plus b, which is 0. And so now we have lost the b that we were trying to solve for. So what has happened? Also, if you evaluate log base 2 of 10/3, you'll see that it is not, in fact, equal to -3. So let me again sort of remind you how to interpret this. We're trying to find values for a and b that make both equations true at the same time. As we're simplifying, the b disappeared and we ended up with a statement that's false. So the way to interpret this is there are no values of a and b that make both equations true at the same time. So, conventionally you could write like no solution, but don't think about that as just like the thing you write at the end of the problem. Like think about what that means. A and B represented particular transformations that would force the curve to go through the points we wanted. So no solution here really should mean that there aren't transformations that will make our curve go through those 2 points. I think it's time to break out Desmos and sort of look at how that makes sense. So here we have it. I've added an A and a B. Here, let's add the 2 points we're trying to force them through. All right, and so you can see the 2 points that we're trying to have our curve go through. So as I move A, we can do this. So I can make it go through the red point, or if I had finer precision, you could see I could maybe make it go through the blue point. If they're going to go through if it's going to go through both points together, it feels like it needs to be kind of upside down, like this. But then I also feel like I need to shift it up so that it can be kind of up here and going down through it. But the other transformation I have can only translate it horizontally. So now we can just sort of see intuitively by playing with it why it should make sense that there aren't values of A and B that would solve the system. It's because like geometrically we can see that there's like these are the wrong 2 transformations to have chosen if we want our curve to go through those 2 points. So this is going to be a big theme of your work later on, is this technique where you make some transformations and you plug in what you know and you solve. You have to think a little bit ahead of time about what transformations make sense. Go ahead and let's try and solve this one. We'll set it up first, and then hopefully you can solve it using the same trick as over here. So a times 2 to the b times 5, and then let's see, 3 equals a times 2 to the b times 8. Okay, so go ahead and try and solve it with the same trick. Pause it. See what you can do. Okay, I'm solving it now. So I'm going to do the same division. So 10/3, a divides a to be 1. And then here I've got, I guess I'll write it out, 2 to the 5b over 2 to the 8b, which is the same thing as 2 to the 5b minus 8b. So now, kind of looking at the left side and the right side, like let's pretend that middle wasn't there. I'll take the log base 2 of both those sides. So log base 2 of 10/3 equals 5b minus 8b is -3b. And so now I can divide by -3 to give me b is -1/3 log base 2 of 10/3. Great. So now I have found my horizontal scale factor. Let's plug it back in maybe here to find the vertical scale factor. So 10 equals a times 2 to the 5b. Let's divide by that. So a is 10 over 2 to the 5b. So I'll multiply 5 by this whole thing. So that'll be -5/3 log base 2 of 10/3. So that's come out, not the prettiest. And this is something where it's, a little bit hard to tell. You can't imagine what these numbers are. But let's plug it back into Desmos. Verify that this makes sense again. So this time I've got a horizontal scale factor of b. And instead of having sliders, let's plug in the 2 values that we think they should be. So I'm copying now off of my sheet of paper. B was -1/3 log base 2 of 10/3. Oops. Okay. And now A was equal to 10 divided by 2 to the power of 5b, I believe. And there we go. We just like snapped it right into place there. And if you want to, you can bring this up on your own Desmos, and you can add sliders for A and B. You can kind of slide them around to convince yourself that those two types of freedom at the same time give you enough flexibility to have your curve go through the 2 points. But that's the thought you want to be having. Could we make it go through 3 points? Like, could we make it go through the same 2 points as before, 5, 10, 8, 3, but then also 10, 6? Here's what it looks like. Hopefully, looking at that picture, you're thinking, hold on, Mr. Dobrovich. There is no amount of stretching or squishing or translating that is going to make this shape fit those 3 curves. And you are absolutely correct. Another way of saying that is, even if we added 3 scale factors, so let's do like a times 2 to the bx plus c. So I've got a, b, and c. This provides a lot of flexibility. I can make this curve look like a lot of different things. But if we were going to set up a system, if I tried to solve this system, I've got 3 equations. I've got 3 unknown things, a and b and c. We can know in advance that this system of equations wouldn't have a solution, just intuitively, because we can kind of see that this shape can't be forced into those points. Okay, now you. Let's do secant. Why be timid? So secant, even if you don't have a picture of this in your brain necessarily, I want to emphasize that these same techniques can apply to anything. I could write some totally insane equation here, and you could still add parameters representing transformations and plug things in and solve. But I do want you to think a little bit, like if we're going to have secant go through these 2 points, you have some choices in what transformations you want to add. So give a couple different ones a try. Some are going to be easier than others. Some might not be possible. As we saw in the last example, if I chose where to go. Yeah, so here when I chose horizontal and vertical, ended up not being possible. So use some amount of judgment in what transformations to introduce, but go ahead, set up some systems, solve them, and then you can double check in Desmos.